basically what we've done is we've gone through every rule. Every of the basic derivative rules, the chain rule, the trig rules, the e to the x, the a to the x, the natural log, the log base a of x, all of those rules. We've gone through all the different rules on how to find derivatives. This is kind of like the last rule that you're going to use for finding derivatives. And this is going to kind of expand derivatives outside of just pure functions into things like conic sections and such. So we can actually find derivatives. But in this case, sometimes we need to know an x and a y value, like a point that's on the graph of, like, for example, a circle, in order to actually calculate what the derivative is, which is what the rate of change of the graph actually is. This is our last step before we get into full-blown application of derivatives. And I've done this a little bit different than I've done in the past. I've hit you guys with as many rules. I hit you guys with the rules first with just the position function application. And there is a heck of a lot more application to it. And I wanted to do all the application instead of doing, all right, here's a rule, here's some application, here's a rule, here's some application. I wanted to kind of do, here are the rules, here's the application of why we are actually taking derivatives in the first place. What is it going to get us? What can we do with it? What are we going to do when it has a real life situation, or if it's more mathematical and we're looking at a function and things of that nature, because there's two different ways to think about it. Now, implicit differentiation means, well, first we'll start with explicit differentiation. This is a situation where you have like y equals 2x. What's y prime? 2. All right, not a problem, right? You know y is a function of x, and you're good to go. Now, implicit differentiation has, let's say you have x squared plus y squared is equal to 16. Now, what is this an equation of? A circle. It's the equation of a circle. So implicit differentiation helps out great when you're dealing with conic sections. When you're dealing with ellipses, circles, hyperbolas, those types of things. Even those wacky sideways parabolas, instead of y equals x squared, you have x equals y squared, which do exist, and we can play around with them. They are, even though they're not functions, they're continuous. And now, I want you guys to not make this difficult, as in everything. The ones that are difficult are your product and your quotient rules, because you got to remember that formula for them. The ones that can get confusing are the chain rules, because there's so much going on, and then you got to figure out, what do I have to simplify to? What don't I have to simplify to? Things of that nature. Like on the quizzes that you took, there were some where, like with the product rule or the quotient rule, you got a lot of like terms that you could just do, and it was pretty straightforward. Like you could do some distributive properties and combine like terms and be done with it. It wasn't major league as far as just absolute craziness like some of the ones that we've seen before. So I want you guys to kind of think of implicit differentiation as not being the most complex thing on the planet, because honestly it isn't. We're taking derivatives with respect to what? X. When we get into things like related rates problems, we're going to take derivatives with respect to time. And so we're going to start talking about things with respect to time and such like that. in those cases, what we're going to do is we're going to look at all these different variables like this, and even the constant, and we're just going to apply the rules. The problem comes into, or the problem that you run into is right there. That is not x, is it? No. So for this term, that y squared, we have to use a chain rule. And it's going to be a weird looking chain rule. But if you remember what you got to do, and it pretty much is pretty straightforward what you got to do, you're going to be okay. Now, x squared. What's x squared? What's the derivative of x squared? 2x. What's the derivative of 2y? If it was just 2y, and I said, all right, here's 2y, what's the derivative of y? Y squared. What would be the derivative of that? I do that a lot. I actually say the answer instead of... Now, is that x? No. So we have to multiply it by dy dx. And this is what sets implicit differentiation apart from all the other ones. Dy dx right here is kind of like saying y prime. It's kind of like saying f prime of x. All that kind of stuff. So that actually is the derivative. And that's going to be equal, what's the derivative of 16? 0. So you take the derivative of everything you have using our derivative rules. When it's a variable, take the derivative of the variable with the rule. And we did that with our y squared. We got 2y. Now what you want to do is solve for dy dx. You solve for that dy dx, and you found the derivative of a it's not a function, it's a relation. You found the derivative of this relation, which just happens to be a circle. And now we'd have a relation that's going to give us the rate of change at any point. The rate of change of the circle at any point. So, how do you do this? What's the first thing we do? Yeah, subtract 2x from both sides. You'll get 2y times dy dx is equal to negative 2x. Now what? Divide by 2y. So I'm going to divide that by 2y. 2y divided by 2y, that's a 1, so they're just going to divide out. So I'm left with dy dx, which is what I want. And that's the whole reason what we're doing is to get dy dx all by itself. And that's going to be equal to negative 2x over 2y, which is negative x over y. And at that point, now we have this wonderful function, or not a function, but we have this wonderful relation dy dx, which is negative x over y. As long as we know the coordinates of the point we're looking for, we can figure out the rate of change of the graph. We can find the rate of change of the circle. And I'll give you a hint. For every circle, it's going to end up being negative x over y. I'm pretty sure. Ends up being negative y over x. Yeah.
What happens if there was more than just one y? Would you plug in dy dx for all of this term?
That is a spectacular question, and it leads into my next one. All right, but first off, this basic idea of every time that we're taking a derivative of something that doesn't have an x in it, but yet the derivative is with respect to x, we have to put this dy dx. Or if there was a w, it would be dw dx. Or if it was an s, it would be ds dx. If it was anything else, we have to take the derivative with respect to x. And we have to put that in there. This is, like I said, going to be a major part of the related rates section. One of the first really big applications of what we're doing with derivatives. So far, so good? Was this horrific? No? Your answer right here is dy dx is equal to negative x over y. That's your answer. Now, if you had, let's say, y to the third plus y squared plus y plus x squared, there you go, plus 2x plus 3 is equal to 10. And I want to know, I want you to calculate dy dx. I want you to figure out the derivative of y with respect to x. Then you say to yourself, oi. But let's take this down to the most simplest thing that we could possibly do. Take a look at that. Can I take the derivative of y cubed? 3y squared, right? 3y squared times dy dx because it's not x. Now, can I take the derivative of y squared? All right, that's plus 2y times dy dx. What's the derivative of y? Yeah, because it wasn't an x. Plus, what's the derivative of x squared? 2x. What's the derivative of 2x? What's the derivative of 3? 0. What's the derivative of 10? 0. Now, at this point, since I want dy dx all by itself, shouldn't I probably get rid of those? All right, so if I subtract those over, can I do that in my head? And rewrite this as 3y squared dy dx plus 2y dy dx plus dy dx is equal to negative 2x minus 2. Now, if I want to solve this, all I did was take a derivative of each term, which was just a power rule, with a little bit of a chain rule when it was y and not an x. Now here, yeah, we can factor out the dy dx. And what am I left with? And that's going to be equal to negative 2x minus 2. And now I got to get rid of that whole thing in parentheses. So just divide by 3y squared plus 2y plus 1. Divide that by 3y squared plus 2y plus 1. And I got my dy dx is equal to negative 2x minus 2 over 3y squared plus 2y plus 1. And that's it. That's implicit differentiation. Now, like I said, this is going to be, like, here's a preview of coming attractions. Well, I'll wait till we get to related rate problems, because I have to install some previous knowledge that you've had before. Not too bad? All right. Now, your homework in your course pack is the implicit differentiation worksheet. It's 15 problems. And I think it's like on page what? 28? 28 and 29? That's what I thought. Page 28 through 29. That'll give you some practice on the absolutely. The rest of the hour is yours to work on this. Yeah. Yeah. maybe 2011 was the last time, 2010. About 4 years ago.